Hey, this is a 4-minute video and I'll be presenting the paper Spectre Attacks. The paper won Distinguished Paper Award for the IEEE Symposium on Security and Privacy in 2019. With the impact of more slow, transistors got smaller and smaller. Lennart Slow says that as the transistors get smaller, the power per unit area remains constant. This means that in order to reduce power, we need to build smaller chips in terms of area. This means that the clock speed can be increased as the size of the processor gets reduced. However, this won't work anymore as the node size has almost reached the limits of physics. There are other issues like leakage currents and heat. Hence, Lennart's law broke. If you see the graph, you see that the clock speed ceased to increase after a point. To overcome this problem, multi-core processors were introduced. The DRAM latency has not improved much in the past few years, which is affecting the performance of the system, as the processor needs to wait for the data it requested when there is a cache miss. A modern-day processor is an out-of-order processor. Out-of-order execution was the solution to the performance bottleneck caused by the speed difference between processor and memory. An out-of-order processor reorders the instructions before it gets executed. Instruction fetch and decode happens in order, and the instructions are kept in reservation stations. The execution of those instructions in reservation stations happens only when all the operands of the instruction are ready. Once the execution is done, the result is broadcasted on bypass network, so all dependent instructions can be signaled that data is ready. Finished instructions are kept in reorder buffer and commit happens only in program order. The obvious question with respect to out-of-order processing is that what happens when there is a branch? Normally, a processor needs to stop execution until the branch gets resolved. But this affects the performance heavily, especially if there are many pipeline stages. A solution to this is to predict the branch and move ahead on that particular path. If the predicted path was actually right, then the execution continues. Otherwise, all the executed instructions have to be flushed out. A recovery mechanism is triggered in that case to restore the state of the processor to the right state after the branch. All the instructions following the branch in the pipeline has to be killed. Consider this code to be in the kernel within some function, and X came from the user, who is an attacker, which is comparing against size of array1 and doing a lookup to get some byte and multiplying it with 512. Assume array2 won't overflow, but array1 has a fixed size. Execution of this code without speculation is safe. The second statement will not get evaluated unless X is less than array1 size. But during speculative execution, let's see what happens. We have code on left and cache memory status on right. Array1 size, let's assume it's 8 bytes. The objective of the attacker is to read some memory which is out of bounds, read from array1 and get the results. For example, reads array1 of n plus 8, which is 09. If statement results false because n plus 8 is greater than array1 size, and this should not get executed. The setup of the attack involves training the branch prediction so that branch predictor expects the if results are true. This is easy to do since branch predictor results are based on previous branch results. Now the attacker evicts array1 size and array2 from the cache, but the secret remains within the cache. Now the attacker calls the API with value x equals n plus 8, which is out of bounds. Speculative execution runs because the value of array1 size is not in cache. The branch predictor predicts that if statement to be true, as in previous calls this was true. Now the speculative execution reads the out of bounds value using x, and the read returns secret byte 09, which is the first byte of the secret. Speculative execution continues and requests memory from array2 base plus read value 9 times 512, which brings that value into the cache. At some point afterwards, processor realizes that speculative execution was wrong since if statement was false and flushes out all the registered changes, but cache state never gets reverted. Later, attacker checks all of 256 possibilities of I values to see which one in array2 is cache that reads fast. For the one that was bought into the cache for I equals 9, that read happens very quickly. Others needs to be fetched each time from DRAM, which takes hundreds of clock cycles. This reveals the secret. Attacker can use different values of X to reveal the whole secret. The previous slides demonstrated just one variant among a wide variety of attacks in this domain. There is a fundamental assumption that a processor will execute everything faithfully, which is proved wrong here. Vulnerabilities arise from a long-standing focus on maximizing performance. Hence, most of the critical components have evolved with complex optimizations, which can expose a lot of security issues. And lastly, Spectre is not a bug since everything works as expected. The contract between hardware and software is broken here. This is a symptom of excessive architectural ambiguity. Thank you.